Okay. At clock period 3 of this instruction, we're doing the add. It takes us 1 clock period, 9.5 nanoseconds, to add two 24-bit operands together. The way we do that is we take and we do part of the add on the way in, and we latch it up right in the middle of the adder, and then on the way out the door, we finish the add. So that by the time we get to clock period 4 here, your add's been completed. And we load A1. So there's the data. We take the data out of the register. I guess we gate it out, huh? We gate the data out of A2 and A3, put it in the readout register, clock period 2. At clock period 3, it's on, in between 2 and 3, it's on the wires, into the module, being added up. By clock period 3, you're right in the middle of the add operation. It comes out of the latches, finishes the add, hits the wires again, it's back onto the module, into the A register, and back in A1 by clock period 4. So it took us 4 clock periods to do a 24-bit add. Well, what about this A1 reservation here? How long do we have to reserve this? I'm getting a lot of different answers here. Let's see. Let's do this once. Let's say at clock period 1 of this one, we've got another instruction in CIP, don't we? Because there's something behind us here. And let's say it's another 030. Only this time we want to use A1 as an operand. Now we'll see how long we need to reserve this, won't we? That's right. A1's not loaded till clock period 4. But I'm going to tell you right now, we don't have to keep A1 reserved until clock period 4. Why not? Because how long does it take us to actually get the data on its way to the adder? It took us 2 clock periods, didn't it? And what I'm going to introduce is something else that they do on here that's kind of tricky to speed things up. What's going to happen at this clock period is we're going to ask the same questions, well, only with different registers here, that we ask at this one, CIP. We're going to say, are there any reservations on A4, 5, or 1? And the answer is going to be yes. A1's reserved because we just reserved it. Just that clock period. So what's this guy going to do? He's got to recirculate, doesn't it? He doesn't have any choice. All right, because the answer was yes here, he said, we'll hold issue across this line, and we'll still be in CIP next clock. Well, what we're going to do now is we're going to play a little trick on you here. Right here, we're going to say, is A4, 5, and 1 reserved? And what the circuitry is going to do is it says, well, let's take a look at this. Let's analyze this condition first. Well, actually, circuitry is already built, but this is what we're designing it now and see what we can do. It's going to take us, if we want to add A5 plus A1, it's going to take us until the clock period 4 of that first instruction to get A5 into the readout register, isn't it? Agreed? All right, so if we issued this instruction to clock period 1 right now, at this time, the next clock, we'd have A5 ready to go. All right? So if we built something into this module so that he could not only load A1, but he could also load the readout register, we could save ourselves a clock period, couldn't we? You see that? So let's do it. Let's see. Okay, when this construction moves to clock period 1, we're going to reserve A4, right? At the same time, we're going to gate A5 so that right here, A5 is in the readout register. Now, all we have to do is make sure at this time we bring up a bypass signal that says bypass A1. We'll generate that because we were in CIP. He says, I know that if you bring up the bypass next clock, what's going to happen is we're going to take this A1 data that's coming here into A1, and we're going to also put it down here into the readout register for that condition, which is the J and K readout. So we're going to just put that data in two different places. That's easy to do. We'll just take a copy of it and we'll just move it right in there simultaneously. What we've done now is we've saved a clock period, and we said, okay, now the next clock period here, we go to CP3, and we can be in the adder. And one clock period after that would be clock period 4, and we'll load A4 up. What that meant then is the A1 reservation, oops, better change colors here. We'll drop A1 reservation, that clock period, so that we can say, okay, it's no longer reserved, so we can issue this instruction to clock period 1, utilize this bypass, and then do this operation and save a clock period. So these registers have this capability. They have that bypass. And it's fairly easy to do. If we look at the register itself, here's an A1 register. And here's a readout. In this case, a K readout register. All we have to do is connect this wire to here, and we'll load both of them at the same time, won't we? Well, it might be harder to do that on the module, but it's really pretty much that simple. Just make a copy of it and send it over to another place. What they're doing is this. When we reserve A1, there's a latch here that says A1 on it. Okay, and we set it. Let's see, how are we going to do this? We just set the Q side of the latch with a clock or whatever. At the same time, we'll call that the A1 reservation. At the same time, there's an A1 request latch. If you have a request latch and a reservation latch at the same time, you drop the issue signal, or hold it. If you don't have this condition where they're both equal to 1, then it's okay to run. But if you have a request and a reservation at the same time, you hold issue. Just like a hotel room. If somebody else is already in the room, you can't have it. You got to wait until they leave before you can go in there. Hopefully they clean it up in the meantime. But anyway.
Is it always in the second clock period that you get the bypass? How do they know when to set bypass?
Bypass is related to the functional unit time. Okay, now all of the functional units are going to take this long. When we want bypass to come up is right here so that we can bypass the data the next clock. All right?
Based on when they know
Yeah.
the results are going to be there, which...
Exactly. Yeah. Now, all the A register instructions are that use functional units are going to be exactly like this. The only difference is the functional unit time. The adder only takes 1 clock. The multiply unit takes a couple more. Takes 5 clock periods, somebody tells me from the back of the room. So, all we have to do is stretch out this window that says functional unit here. In this case, it was the add. All right. Now, we were loading up A1, and at the same time, we were taking stuff out of A5. That doesn't sound to be a problem. But what about, well, maybe I'm going to have to clean up the board here. Well, maybe not. Let's do this. Let's say at the same time that we were loading A1, we had started a long time ago a memory operation. Remember that one we started where we read A4? Well, it's just finishing now. Okay? What happened is it took us 14 clock periods before the data came back. And now here comes the data. At the same time, data for A4 and A1 is coming into the same modules effectively. Is that possible? Can we do that? Yes, you can. On the cray 1S, you couldn't. And some of you have learned about the cray 1S, or at least watched the tape. But now you can do it. You can load A4 and A1 at the same time. In fact, as many functional units as you can find, if we would have issued a multiply ahead of time, we could have loaded another A register at the same time. There's multi-buses in. There's as many paths into there as you want to use. There's a couple of little exceptions, but that's minor. There's always exceptions. There has to be. Wouldn't be a rule otherwise, right? Oh, I screwed up, didn't I? You're right. Well, wait a minute, though.
Now, did we reserve A4 back when we issued the memory and stuff?
Yeah, we would have, but we would have released it already by now.
Okay.
Now, because we're not going to reload A4 until way out here, so we're not using A4. Now, it's kind of dumb, but a programmer would probably do it. You know, it could happen. You load A4 here and then reload it just to make sure, you know. I don't know. Yeah, I should have used a different example. Just ended up to be A4. I'll change it. A3. Now it makes more sense. It still would have worked.
You might have needed that one clock period in between.
Yeah. It might have worked, but I doubt if you'd be able to pull it off. Okay. Okay. There was also a question about A1 and the K readout register. That was a pretty good question. Here I loaded an A1 register. That's a register that's actual existing register somewhere. There's 8 of them, A0 through 7. I can load that register. At the same time, the data that I'm putting in A1, I can put in this K readout register. I used the A1 to signify it here, but actually it's a different, separate, and distinct register. There's an I, J, and a K readout register. There's 3 of them associated with the A registers that you use to move stuff from the register to a functional unit. It always goes through the readout register. Okay, I'm going to do one more A register type instruction. That's the 032 instruction, which is a register multiply. And that should be on the next page of the hardware reference manual. So we're going to put an 032 instruction, 4, 5, 6, in the CIP register. When it hits CIP, the first thing we do is we decode the instruction. The reason we have to decode the instruction is we have to know what functional unit we're going to use. We also have to know, are we going to use all 3, the I, J, and the K? Some instructions maybe you only have 1 operand register. For a shift, for example, if you were doing a shift, you only need 1 operand and you shift it to another result register. But for right now, we decode this and we say it's a multiply operation. We're going to take A5 times A6. Remember, it's the contents. That's what these little parentheses mean. It's the contents of A5 and 6. It's not the 5 and the 6, but it's whatever they're equal to. All right? And we're putting it in A4. When we do that instruction, what do we have to check on reservations? What do we have to check for reservation? Yep. check reservations. A4, 5, 6. Any one of them being reserved is going to hold this instruction in CIP. It's going to drop issue. When this moves to clock period 1, what do we reserve? At the same time we reserve A4, we gate A5 and A6's data. We gate it off to the readout register. A5 is going into the J readout, A6 into the K readout. A5 is going into the J readout, A6 into the K readout, so the registers are loaded now with the data that was in A5 and A6, whatever that data was. Okay? At clock period 3, we hit the functional unit. We're doing a 24-bit operand, two 24-bit operands times one another to get a 24-bit result. That takes 3 clock periods. Now, we reserved A4 here at clock period 1. How long are we going to have to hold it? How long did we hold it for the adder? We held it until we were 2 clock periods away from using it, loading it, right? So we're going to hold it here. Here. And here. Right? Is that right? We're going to drop it there. Now, if an instruction was right here at clock period 1 that wanted to use A4, any type of a reference, if he was going to use it as an operand, he would say, okay, I want to use A4, I want to use A4, I want to use A4. Gate the other one, A4 will be meet me in the readout right there. By the time somebody, if they were using A4 as a operand register, you see, A4 is going to be loaded by the time you can get that instruction issued anyway. All right? And if you were to have a 030 here, let's do that. Let's put an 030 as the next instruction. One, two, 4, which is a logical thing to do. We've multiplied 2 operands together. We've got an answer in A4, and now we want to add something else to that answer and put it somewhere else. That's logical. This clock period, it's in CIP. It's not going to issue. We're going to hold the issue signal, and we're going to keep it in CIP. The next clock period, we're still going to keep it in CIP. At clock period 4 is when we're going to release the reservation, isn't it? So that this instruction can then issue to clock period 1 at time 5 overall here, or the clock period 5 of the first instruction. Okay? So how it's going to work here is we're going to hold issue for 1, 2, 3 clock periods on this instruction. We'll then, 1, 2, 3 clock periods on this instruction. On the 4th clock period that this is in CIP, in other words, it stayed in CIP for an additional 3. The 4th clock period that this is in CIP, that A4 reservation is released. We generate at that time the A4 bypass signal. We advance the instruction to clock period 1. We gate A2's data off to the readout. At the same time that the data is coming in from the functional unit to A4, it's also going to be loaded into the K bypass again. Once again, we're going to put the data in 2 different places. That's why we can release a reservation at clock period 4 time. All right. Now, if you wanted to use A4 as a destination, again, it's certainly going to be available by the time you get any data created to put in it. No. No, if this, in other words, reverse these. So it's 4 and 1, like this. Yeah, that would still work. It would still release here. Now we gate A1 and A2 off. A2 and A1 would be in the readout. The next clock period we do the add. The next clock period we load A4. Okay, so the rest of it will run just like that. The reservation is dependent only on the functional unit time. It says we reserve the functional unit at clock period 1 and then hold it, the reservation, for as long as the functional unit takes. I think that works. No, it does not. We reserve it and hold it for as long as the functional unit takes. So we set it here at clock period 1. Now we just hold it for 3 clocks because that's how long the functional unit time is. 1, 2, 3. We release it. It runs. Takes off. On the add, the same thing takes place here. Let's see. I'll switch colors in midstream here. Would we load A1 first time? Whatever. The same thing here. We reserved A1. We held it as long as the functional unit time, which is 1 clock period. Release A1. And it'll run to completion. Another instruction following here, wanting to use A1, would issue right there. Okay? Now you can chain as many of these instructions together as you want. And they should all figure out roughly the same way. The only variable is the functional unit time. If we're doing a memory operation, the functional unit time is, what, 14 clocks, something like that anyway. I'm certainly not going to time one of them out on the board. I'd be halfway down the wall over there before we finished. So that's the A registers. Any questions on the A registers or their issue of instructions? If you use A0 as a J or a K operand, you don't get the value of A0. You get instead a value of 0 or 1, depending on where you put it. Is that right, John? 5-5? Okay. I didn't know where it was in a hardware reference manual. Ah, there it is. And what that says is, if you use AI equal to 0, where I is equal to 0, you use A0, don't you? If it's used as an I register, you get a value into there, whatever you wanted. You get A0, the contents of A0. if aj equals 0, you get a value of 0. If ak equals 0, you get a value of 1. So for that case that I picked where I said you take A1 and add it to A1 and put it in A1, actually what you would get is a value of 1 for the K field. Right? No, you wouldn't either. That'd work. If you used a 0 in the K field rather than the 1, you'd have a value of 1 added to the A1. All right? For example, let me show you here. Let's take this instruction right here and make it look like that. If I put a 0, I'll highlight it. If I put a 0 in the K field here, rather than taking the contents of A0 and gating it out, you gate a value of 1. And you put into the K readout here a value of 1. So that when you do this add, you take A2, whatever it is, add 1 to it, and put it back in A1. So A0 cannot be used as an operand, can it? Well, you can, and you just don't get the value of A0. You get something else. Any question on that? It's a special case built in for increment. Now you can do an address increment with that instruction. All right. Any other questions about address registers? Okay. Now the same thing holds true for S registers. You get different values than the value of S0. Let's talk about the S registers then. There are 8 S registers, S0 through 7, just like the A registers. The S registers, however, are 64 bits in length. So that's one difference. Associated with the S registers are some T registers. The T registers are just like the B registers in that you can block load them from memory. You can do a block size of anything between 1 and 64. They are circularly filled. You can start at T77 if you want and have a block length of 64, and you will fill T77 through T76. And T77 will have the first word that you wanted to transfer, or any variation thereof. Once you do load up the T registers, you have the instructions that will transfer a T register to an S register. Once again, you can use it as a buffer for memory data. You can load up all the T registers in the same amount of time it took you to load the B registers, but the T registers are 64 bits, so you get the whole memory word this time. You can transfer them in. It takes you the startup time of the T registers plus 63 more clocks to load them all. And now it takes you a 1 clock period instruction to issue and move a T register to an S register or S to T register. The S registers have their own functional units. Just like the A registers did, it has its own functional units. You have an S register add unit. This does a 64-bit add. You take 2 64-bit operands, add them together, you get a 64-bit result. Once again, no overflow detected. It's an integer add. You also have a S register logical functional unit. It does ANDs or ORs or exclusive ORs with 64-bit operands. So you can AND 2 64-bit numbers together and get an answer back. Or do the exclusive OR or the inclusive OR of 2 64-bit numbers. There's a bunch of logical type operations. You also have an S register shift functional unit. You can do right and left shifts of data. In other words, shift the S register data right or left X number of places. You also have a population count and a leading zero functional unit. The population count, in other words, goes into an S register and counts the number of 1 bits set in that register. Right, John? Good. The leading zero functional unit looks at an S register and tells you how many leading zeros are in that S register. How many zeros until you get to the first 1, in other words. I'm not exactly sure what they use that for, but that's what the functional unit does. Now, the S registers also have access to the floating point functional units. You can take an S register value, or 2 values, and send them to the floating add. And it says that you have to have those S registers in floating point format. There's a specific format for floating point numbers. It's explained in the hardware reference manual, but it's the first parcel, parcel 0, is set up as the exponent of the floating point number, and parcels 1, 2, and 3 is a coefficient. It works somewhat like scientific notation, only it's in the 2's format. So it's 2 to the 16 or 15 bits of power that you can have there. You can get a pretty good sized number anyway. You can do a floating add, you can do a floating multiply, or you can do a floating reciprocal approximation. 1 over a floating point number, in other words. It's an approximation. It's not exact. It's only accurate to what? 48 bits or something like that? No, 30 bits. So it's not exact. It's only accurate to 30 bits. Close enough, though. The reason we do a floating point reciprocal rather than a divide, why we have a reciprocal functional unit rather than a divide unit, is because you can fully segment a reciprocal unit. If you do the reciprocal and then do a multiply, you can do the same thing as a divide. There's a formula that worked out that you can do that. But you can fully segment a multiply unit. You can fully segment a reciprocal unit, but it's very hard to fully segment a divide unit. So when Seymour came up with the cray 1, he said, we're going to have a reciprocal unit. And that's what this has. Any questions on the S registers or their associated functional units? Now, the S registers are sharing the floating point functional units with the vector functional units, or with the vector registers, I'm sorry. The S registers and the vector registers share the floating point functional units. Either one or both can use them. Not both at the same time, but either one of them can use them. "64 bits in length. There's 8 S registers. There's 64 associated T registers with them. Any questions about the S registers? They're almost identical to the A registers. The only difference is they got 40 more bits. Other than that, they're the same. The modules are almost identical in Boolean wise. You look at the Boolean terms for a GR module, which is the S registers, and an AR module, which is the A registers, and the Boolean's almost identical. The only difference is there's more GRs, because there's more bits. Let's look then at the issue of an S register type instruction. And we got a couple of new types of instructions that I'm going to introduce now too. The first one will stand by the old add instruction, and that's a 060123. It should be on about page 5-60 or so, huh? Nope, 5-50. This is an S register add. Once again, it's this integer adder. S2 contents plus S3 contents to S1. When this instruction is in CIP, what are we going to have to check for reservations on? S1, 2, and 3. In other words, it's the same as the A registers, isn't it? It's the same thing. What about the S functional unit? S register adder. Do we have to check and see if that's reserved? No, it's fully segmented just like the A register adder, and it's a separate adder. So that's no problem. So if we do this instruction, and we have none of these reservations, this instruction will then move to clock period 1. When it hits clock period 1, the first thing we're going to do is reserve S1. Do we have to reserve S2 and S3? Why not? That's right. Exactly. At the same time that we reserved S1, we're going to gate S2 and S3 off to a readout register. We're going to put S2 in a J readout register, and this is a different readout register than the address one. This is for the S registers. And we're going to put S3 in a K readout register. At clock period 3, we're going to be in the adder. I think this one takes 2 clock periods. So what was the big difference between this and the A register add? Well, first of all, we had another different bit set in the G field, and it takes 1 more clock period to add those extra 40 bits together, because all the sums and carries and stuff that we got to pass on down the line, it takes another clock period. Other than that, everything's identical. We can still use the bypass. If we have another 60 instruction here at clock period or at CIP time, it's going to be held for functional unit time again, so S1 is still reserved. At clock period 3, we'll release it. And generate the bypass signal if there was an instruction waiting to use S1. I'll put it in here. But remember, that's conditional on somebody needing it. It only gets generated if you need it. Well, that makes sense. Don't bypass it unless you have to. We would then, if you were going to bypass S1, we would load it into S1 and into the readout register if necessary. Any question on that? Last time we looked at the functional unit, the longest functional unit time we had was memory, wasn't it? Well, now in the S registers, because of the floating reciprocal approximation, our longest functional unit time is going to move to that. The functional unit time for the floating point functional unit is, let me look it up here, 13 clock periods. So it takes 13 clock periods inside a functional unit. So the only difference between floating point approximation and an 060 is another 11 clock periods in the functional unit before we get our result. That means that we'll have to hold our reservation for a little longer, won't it? Probably 11 clock periods longer. Once again, once the data gets here, we can bypass it. Once again, we can load data into S registers from any one of the functional units that you can think of. Once again, there's a couple of little exceptions, but you don't have to worry about them usually. Somebody look up a floating add instruction. I think it's like a 62? 62, huh? Well, let's put a 62 instruction here. 062. 062, 1, 2, 3. Well, this should be easy to do. Let's save some of this stuff. There. So what we're going to do is we're going to take S2 and S3, we're going to add them together, but we're going to have them in floating point format. In other words, part of the S2 and 3 are going to be exponent and part are going to be coefficient. And if it's a floating point number or a scientific notation number, you have to treat the exponent different than you do the coefficient, don't you? You have to have, I don't know, I don't remember what you do. You add, subtract, divide, something. I don't know. They have to be equal or something, don't they, before you can add them? Shift them? I don't remember. Something like that. You do something with the exponent that you don't do with the coefficient. I know that. But anyway, when we issue this instruction, when it's in CIP, what we're going to have to do is make sure that S2 and 3 and 1 are all available. What about the floating point functional unit? You have to check and see if that's available. Why? Exactly. A vector operation might have been using this floater adder. Remember, they share them. And if he was using it, remember, the vector registers can do more than just one single operation. They can do a multitude of them. So you have to make sure that the vectors aren't using it and don't have it reserved. If they did have it reserved, you'd wait until it was done and free. And once it is free, then you'll issue your instruction. That's one difference. The S registers have to check and make sure that the floating point functional units are free before they can use them. When this instruction issues to clock period 1, we're still going to reserve A1, or S1. We're still going to gate S2 and S3 off to the readout register. At clock period 2, the readout register is going to be loaded. Now we're steering this readout register to a different functional unit. We're telling him, don't send it to the adder, the scalar adder, send it out to the floating point adder. At clock period 3, we're still in the functional unit, but now it's a floating add. And the floating add takes 5 clock periods rather than 2. One more. Whatever it is they got to do with the exponent takes a long time anyway. I don't know. The floating adder takes 5 clock periods, so we're going to hold the reservation on S1 a little longer. How long? 5 clock periods. We'll release S1 reservation at clock period 6. We'll generate a signal that says enter S1. We'll fan out that enter S1 signal here, and we'll load up S1 with the data at clock period 8. The scalars are only sending these two operands off at the same time. So if you had a vector floating add instruction sitting here in CIP, by the time he gets ready to use the adder, which would be 1 clock period later here, you're already advanced into the next set of latches. Okay? The only time in other words, the only time you have to reserve a functional unit is with a vector operation. Okay? We have to check to make sure it's free, but we don't have to reserve it there, yes. And the only reason we had to check it is because the vector could have reserved it on us. Okay. Now, I'm making these all up as I go along. Is anybody checking me in the hardware reference manual? It tells you exactly how long it takes in the hardware reference manual, doesn't it, before SI is available? What's it say?
6 clock periods after issue.
6 clock periods after issue. Well, we know it takes 2 clock periods, this startup time here. So it takes 1 clock period to issue the instruction. The next clock period, we've got to gate the data out of the readout. 6 clock periods after that, SI is there. But when was SI available? Clock period 6 here, wasn't it? So you can get 2 pieces of information off of there. You know SI is available right here. If you want to use SI, or S1 in this case, it'll be free. Why? Because you're going to utilize bypass, aren't you? But when can you actually look at the data in S1? Well, you better wait another 2 clocks or you might not see what you think you're seeing. If you were to scope it or something like that, look at the data. Okay? Any question on that? Didn't confuse anybody yet? God, I gotta work harder, I guess. We're getting to vectors, though. Okay, there's one other kind of instruction I want to look at. Maybe 2. Any questions on this? Once again, if you're going to utilize bypass, if you have an instruction here, maybe let's see what would be a good instruction. Let's say just a scalar add with the 060 instruction issued here. Wanted to use one of those S registers, or wanted to use S1 of those registers. He'd sit here in CIP for a few extra times, waiting till it's available. Remember, before you can let an instruction leave CIP, all the resources have to be there and available. We can't interrupt this instruction. Once it leaves CIP, it's gone. It's going to take exactly 8 clock periods to finish that add. No more, no less. So if you want to use S1, you've got to wait until clock period 6 before you can have him. This computer is really easy, isn't it? Yeah. 036 instruction. Let's take a look at it. I'll have to write it up here and explain it first. 036, let's see, I, J, and K. First thing I'm going to tell you is it's a memory read. Is that correct? It's a memory read? Yeah, okay. It's a memory read operation to T register specified by the J and K field of the instruction. I told you there are exceptions. Here's one of them. Well, if we're going to read memory, and remember I've been mentioning that this is a block transfer all the time, and we're going to take that memory data and put it in TJK, we've got to have, first of all, an address. Where in memory do we want to go? Well, where is the address? The contents of A0. All right, so that means I've got to draw a picture of memory here. just a big empty spot to store stuff, right? That's all memory is. So we've got to have an address here. Let's set, for this particular instruction, A0 equal to 100. Nice round number. Over here at memory address 100, we've got some data. Some X's. X's and O's. Or 1s and 0s, whatever. We want to transfer address 100's data into T register JK. Well, let's give JK a number. Let's give that a 20 octal. So here's our T registers. We're going to come here at 20. We're going to put this data in there at location 20. Now, what do we got to have if we're going to do a block transfer? We've got an address, we've got a register. What else do we need? Yeah, we need a block length, don't we? What's the block length equal to? The contents of AI. Once again, we'll give this an A4, the old infamous A4. So the contents of A4, let's set A4 equal to 100 octal also. What does that mean? That means we're going to take this block length, and every time we transfer one word out of memory and put it in a T register, we're going to subtract 1 from it. As soon as we get it down to 0, we'll stop. Well, if that's the case, we better make our A4 equal to 77 then, huh? I guess it wouldn't matter. Depends on whether you increment it or decrement it before or after you did it. I don't remember which they do. They do it after? I think so too. 100, okay. Whew. These little things you forget. Oh well. Close enough. So we're going to take it out of there. We're going to take the data out of address 100. We're going to put it in T register 20. We're going to increment our T register number. So now we'll put the next one at 21. And we're going to come down here and add 1 to 100 and get 101. We're going to take that word and put it down here. So I'll put 100's data here, put 101's data there, and continue on through until I get all the way wrapped around at location 17 octal here in the T registers. What word am I going to have there? 177. The contents of 177. So it's going to wrap all the way around. Does everybody understand how that worked? All right, now that we've talked about that instruction, let's go back here and stick it in CIP and see what happens. So we had an 036 420. We got to check for reservations on what? What? T registers. Now, there's two ways you could do this. You could have a reservation for all 64 T registers, or you could have one big reservation where you're using the T registers. And that's what they did. They said if you use the T registers, whether you're using just one of them or if you're using all of them like a block transfer would, and that's the normal way you'd have to reserve them anyway, there's one reservation flag that says they're in use and you can't use them. So if you're doing a write to the T registers, you can't read them. That makes sense. Or if you're doing a read, you can't write them.
So you can't just reserve one or two?
No, you reserve them all. Okay. Anything else we have to reserve? Well, we have to check for reservation on A0. Anything else? A4. Anything else? Memory. All of memory? Which port? Right. Okay. Once we decide that all these resources that we need to execute this instruction are available, we take it off and do it. If they aren't, we just wait until they are. Once again, it's that simple. There's a latch, a request and a reservation latch that we compare. If they're both set, we wait. If they aren't both set, we go. Now, when this instruction issues, what are we going to reserve? T registers. I'll put an S behind that so we know. Do we need to reserve A0 and A4? That's right, because they're being really used as operands here, aren't they? We're just going to take a copy of what was in A4 and what was in A0 and move it off to some register somewhere else. And so, for that reason, we don't have to. That was a trick question. Right, so we don't have to reserve A0 and A4. Anything else? The port. We'll reserve port B. Now, how long are we going to reserve port B in the T registers for?
113 clock periods, something like that.
113 clock periods? Can we predict how long that reservation has to hold?
We know it's an A0.
What about all those memory conflicts and stuff I was telling you about? Yeah. What we're going to do is we're going to keep these reservations for block length. We'll hold them until block length are equal to 0, but because of the fact that we could have bank conflicts with other types of references and the other CPU might be doing fetches or something on us, we can't predict how long this instruction is going to take to finish. We know it'll finish. We know it had all the resources before it left here. But exactly how long might be hard to predict. The only way we can predict it is to make sure that nobody else is doing anything. In other words, no other memory references. Then we'll know exactly. And the other CPU is not doing any memory references. That's pretty hard to predict in a real world, but when you're trying to work on a machine, you could do it. You could force it to happen. The one type of instruction we haven't talked about yet is a two-parcel instruction. And now is a good time to do it. Sucker shot. What I'm going to do now is I'm going to bring in a specific two-parcel instruction, and the one I'm going to pick is going to be the 120 instruction. So if you look that up in a hardware reference manual, on page 5-62, you will find that there's several 10H through 13H instructions. They're all listed as a group, and these are the A or S register, read or writes of memory. The one I'm picking is a particular one, the 120 instruction. Here, you will also find it called the 12H instruction. I, J, K, M. It's a two-parcel instruction. In this case, I've assigned the H value, or the H field of the instruction, a value of 0. When you use an AH, in this case it's an AH value that you're using, when you use an H as a 0, you get a value of 0. In other words, what you can do is you can take this H and add it to some other number to come up with an address. All right, more on that later. But for right now, it's a 120. The I field is once again the destination register, where we're going to put the memory data. S5. The J and the K and the M portion of the instruction is going to be the address that we're going to. The J, K, and M. And if you take the 16 bits of the M plus the 6 bits of the J and the K portion, you get 22 bits. Whew, made it, huh? We can reference then anywhere in memory with this J, K, or M portion of the instruction. Once again, just like every other instruction, this J, K, and M, or address, is going to be relative to a base address. In this case, once again, base address is going to be equal to 0. So I'm going to assign a JKM value. I'm going to call it a 100, our old 100 memory location. We accessed it before with that B&T register transfer. So the first parcel of this 120 instruction, which is read memory to S5. And we have to have an address. So we're going to read memory address 100 to S5. When the first parcel hits NIP, we decode it as the first of a 2-parcel instruction. Well, what does that do? We open this little switch. It says when we advance this 10500 to CIP, at the same time, out of the buffer is going to come our M portion. All right? Any questions so far? So let's do it. 120,500. At the same time, down into LIP is going to be our 100. And some leading zeros. What's in NIP then? That's right. Nothing. All right, now we've got this instruction in CIP. Now we can check for a reservation and conflicts on those reservations. First of all, what is one of the reservations we have to check? S5 busy. If S5 is already reserved, busy with some other operation, we won't be able to issue this instruction. What else do we have to check? Right. Port A or B or C busy. If there's another reference of any type, block transfer reference ahead of us that's reserved, port A or B or C, this instruction will stay in CIP until that condition goes away. If there's nothing else stopping us, this instruction will then issue. So it moves to clock period 1. The 1205 instruction portion of the instruction goes off to the control. It says we want to use S5. We got to reserve S5. We have to also stop any block references for 3 clock periods. For 3 clock periods. Stop any block references for 3 clock periods. And that's all we have to do. But we also take this 00 plus the bits of the 100 here and ship that off as a memory address. What we're going to do is we're going to reference address 100. We're going to take the data that's in that address, and we're going to put it in S5 eventually. This takes 1 clock period to issue. The next clock period is the first clock period of the 2 clock periods of address generation and memory timing. Okay, so from here now, we say generate the address for 1 clock, generate the address for a 2nd clock, select which address we want to use, fan the address out for 2 clocks, 4 clock periods of address on chip, 2 clock periods data fan in, 2 clock periods error correction, 1 clock period of data steering, and out here somewhere, right about there, the data is going to hit S5. All right? Any questions on that? When are we going to drop the reservation on S5? 2 clock periods before it gets there. Exactly. What about the memory reservation that we've got? Kind of a memory reservation here. When are we going to drop that? We only delay it for another 2 clock periods, don't we? 2 more clock periods, 1 more clock periods, and now you can issue a block transfer. Okay. Well, let's advance this 1 more clock period here. We're in our first clock period. First clock period of address generation here. What's a clock period 1 then? The blank instruction. All right. Any questions on that? Any questions on a way a 2-parcel instruction is going to issue? Let's say, for example, that we have another 120 instruction here. Let's say it's even to the same bank, just a different S register. We're going to load S3 with the same data that's in location 100. The first time this is going to hit CIP is when that first instruction is at clock period 2. And now we sit here and we say, is S3 busy? Well, let's say no. How about ports A, B, or C? Is this instruction going to issue? Well, remember what I said out here. Stop any block transfers. Is this a block transfer? No, so it's going to issue. So we can get another scalar instruction issued. Why? Because of the fact that it's not a block transfer. Once again, when this issues, then we'll keep any block transfers out for another 3 clock periods. Okay. Well, should we carry it 1 step farther? What the heck? You haven't been confused yet today. Okay? So, there's a third S register read now. We say, is S1 busy? No, it's not busy. How about ports A, B, and C? No, I didn't reserve them. Can I issue this one? On the next clock we can issue it, except for one minor little point. And that is the fact that everybody's been going to the same bank. At clock period 3 here, we had reserved bank 0. Clock period 4, we'd reserved bank 0. Now we want to use bank 0 here, and it's going to generate a bank conflict. It says this guy can't advance to use bank 0, can he? Because we've identified that there's a bank conflict here. You're using bank 0 here, and you want to use bank 0 again with address 100 here. Well, don't you have to have 4 clock periods between references to bank 0? Or add 2 to this? Or put 2 more clock periods in here before we can go? So what we're going to do is we're going to stop this one and just hold it for 2 clocks. So that we solve this conflict that we have over bank 0 that way. In this one, they said at CIP time, if we're already holding one at clock period 2, I give up. I can't handle anymore. We'll just hold this one at CIP until that conflict goes away, and then we'll continue on here. Okay? So, if you didn't have the bank, if you're going to different banks every time, you could just keep issuing these every 2 clocks until you ran out of S registers. So we still have our bank conflict, and we have to solve it some way because of the fact that you can issue scalar references, A or S register references, every 2 clocks. The only reason it's every 2 clocks is because of the blanks in between them. Now, I can take LIP out of here. This is exactly how it works on the machine. Actually, the cray 1S actually worked this way. There was an LIP and an NIP. But now on the XMP, they said, why waste all this logic when we're just going to have this blank condition here anyway, so we'll use it as LIP. And just do this. It's going to work the same way, it's just what you call it at any one time. When we put the second parcel in here, the M portion of the instruction, we tell this little set of registers here, now you're LIP rather than NIP. Okay? At the same time, we generate a signal that we send to CIP that says NIP is blank. We generate the blank NIP signal. Okay? Works the same way. Now the next clock period, when this is advanced out of here, there's the absence of an instruction in CIP. And now this is back to being NIP. We have a new instruction in there. Meanwhile, the M goes out at the same time the first parcel does. So it works the same. Whether you want to put a box down here or not, it works the same way. That's why in the block diagram it's like that. Actually, in all reality, there's only one register there. And it's just whether you call it NIP or LIP, which you use it at any one time, is what it is.
And this is on our map here of what they say lower and upper NIP?
Yes. It's the same set of modules, in other words. Was it H, B, and C? Okay. Any other questions? Okay, so that concludes our discussion on A and S registers and memory and fetch. We've covered all that today. However, I guess I might as well give you a little exercise to take home and think about tonight.
Here is videotape exercise number 1 for A and S registers. The P register equals 12371 octo parcel 1. Now we'll do a fetch operation to buffer 0. What first and last word addresses will be in buffer 0? And what will I bar 0 be equal to? This problem is also found in your course materials. Here is videotape exercise number 2 for A&S registers. Here are 3 instructions: first, second, and third. How long in clock periods till A7 is valid from issue of first instruction? These problems are also found in your course materials. Please stop the videotape and work out the problems in your guide. Restart the tape player when you're ready to go through the answers.
Okay, yesterday I asked you, at the end of the day, I said I'd given you a P-register address as an absolute address here. If you do a fetch based on this address, what's the first address, or the address of the first word, and the address of the last word that's going to be in buffer 0, if you fill buffer 0? Any question on how to do that? Everybody get an answer to that? What'd you get? 12340 is the first address. What'd you get for last address then? 12377. Any problem with that? Any question on how to do that? It's always on 40-word boundaries, isn't it? Every fetch we do is on 40-word boundaries. So if we take memory and divide it up into 40-word boundaries, starting at 0 through 37, 40 to 77, and just keep on going through memory, you end up that the last 2 octal digits of any memory address are always going to be either 0 or 40 and 37 or 77 in the buffer then. We always fetch on 40-word boundaries. So we say, we want 40 words. Where is address 12371? Which 40-word group is that going to be in? Well, that's going to be in this 40-word group, isn't it? 71 there. 12371 is going to be found in that group of 40 words. And we're going to fetch this group of 40 words rather than 40 words starting some other boundary. Does that help at all? Okay. Any other questions? Does everyone understand then? We fetch a 40-word group, but it's always on the same boundaries. And we force those boundaries by just saying, if you look at memory, it's already got 32 banks in it. Those 32 banks have already done the 40-word boundaries, haven't we? We just go and we say, give us one word out of every bank based on this address. And we just look at the upper portion here. 1, 2, 3, 4, X. We say, starting at this address, this is a bank 0 address, isn't it, if we go with a 0 here. Now, give us one word out of every bank starting at that address. And so we get, this is a bank 0 address, we get 41, 42, 43, all those come out of sequential banks after that. Okay? Any question on that then? Does everyone understand how to do that? I'll give you another one, you could whip it off. No problem, right? Good. All right, now I ask you another question. And I said, now we're going to fill I bar 0. We said, after we fill an instruction buffer, as soon as we're done with the instruction, the fetch operation, we take a portion of the P register and force it into I bar 0 so that we can compare it every clock period to see when we have coincidence. Well, what are we going to have? What value is I bar 0 going to be equal to then? Two, 4, 7. Right? But that's in binary. Does everybody agree with that? A 247? What we do is we take this P register address, and I'll write it down in binary here. All right, so here's our 1, 2, oh, I got a couple extra spaces in here. 1, 2, 3, 7, 1. Now, this is 2 to the 0. 1, 2, 3, 4. Let's see, 0, 1, 2, 3, 4. 2 to the 5th is right here. I used to have another colored marker here. Here we go. All right? Everything below this is bank address, isn't it? We take from 2 to the 5th on up, and we stick that in I bar 0. And if you reconstruct this as a octal number, you get a 247. Now, you didn't have to. You could have given it to me in binary, but 247 is easier to work with than a 0, 1, 0, 1, 0, 0, 1, 1, 1. Any question on that? Does everybody see now how we can get coincidence out of this? If I write my P address up here again now, well, I'll change this. Let me take this. Remember, from 2 to the 5th on up is what we put in I bar 0. If I increment this now, to, this would be 1, 2, 3, 7, 7, parcel 3. Once I get to parcel 3 and add one more to it, what I'm going to get is all these, oops, it should carry all the way around now, huh? 0. It's going to propagate all the way up to this bit, isn't it? And now if I do my bit-by-bit comparison, I no longer have a match, do I? I say I used to have a 247 in there, and now I've got a what? 250 octal number. They don't compare. What does that mean? I have to do another fetch. If I just filled buffer 0, where would the next fetch fill? Which buffer? Buffer 1. Exactly. What we do is when a program comes in, the first fetch is always forced to buffer 0. Remember, I told you that there's a 2-bit counter that controls which buffer you load. That buffer pointer is cleared every time you bring a program into the machine. So every time a new program comes in, you clear that buffer pointer, or set it to 0. And now when you do your first fetch, you fill buffer 0. In addition to clearing the buffer pointer, you also clear all those buffer valid flags, that upper bit or lower bit of the I bar, so that you don't have any, you say, I don't have any valid information for this program in these buffers. And so you go to buffer 0 first, and then to 1, and then to 2. After that, it's just an incrementer. So then it goes 0, 1, 2, 3, back to 0 again. Now, I also gave you a sequence of instructions, and I said I wanted to know how long it takes these instructions to complete effectively. What were they? The first one was at 032. All right, well, let's start right out and put this at time 0. This will be in CIP. If this is the first instruction out of a buffer, it's going to issue because there can't possibly be any conflicts, can there? And I told you this one was the one that was at 12371-1, was it? 1. Okay, that instruction is at that location. So it's the first one out of a buffer. So there can't be any conflicts. So it will issue, go to clock period 1, at which time, what do we do with this instruction? Reserve A1, we gate 2, and 3. A1's still reserved at clock period 2, isn't it? A2 and 3 are in the readout at clock period 2. Clock period 3, where's the data? It's in the functional unit. I'll just put that up, it's easier than spelling out multiply. How about A1? Is that still reserved? Okay. I'll just write up A1. Okay. Clock period 4. Well, wait a minute. It's in the functional unit. CP6. Now, there's a question arises here. How long does this functional unit actually take? Now, I told you yesterday in the lecture that it was 3 clock periods, but there's another way you can find that information out. In the hardware reference manual, it lists how many clock periods it is until the data is ready. Now, what this hardware reference manual is written for, if you look up in 032, it should say AI ready in 4 clocks. What that means, it says we're telling some programmer, if he needs to know this information, if he needs to use A1 here, it's going to be ready in 4 clock periods. In other words, if he had an instruction that he's going to follow this 032 with, and he wants to use A1, that instruction won't leave CIP until after clock period 4. That indirectly tells you how long the functional unit time is, because what it's telling the programmer is if you issue an instruction here, it's going to be, remember it takes 2 clock periods for any A register instruction to get out of this readout register anyway. So it says we're going to be out here in 2 clocks, and that means the functional unit time, if you subtract the 1 clock period for the storage in the register, we know they all have this 2 clock period. That tells you there's 3 clock periods in a functional unit time. In other words, it says AI ready in 4 clocks. If you subtract 1 from that, you get the functional unit time of 3, which is exactly what this is. And that number, that AI ready, is what you can depend on in all cases as the functional unit time. They said the startup for any A or S register instruction is always the same. It's always 2 clocks. So it's going to be in the result register in 4 more. Subtract 1, you got the functional unit time. What do we care about? We want to know how long that is so we can figure out this instruction in this case. If you were working on a machine and you were dropping or picking a bit in this multiply, what do you want to know? You want to know when is the data going to be here in the result register so I can look at it with a scope probe and see if it's right or not. And if I know when it's there, then I know I can go back 1 clock period in the multiply here and look and see if I'm doing it right. Or I can go back another clock and say, well, it's there. And I can go back another one and say, oh, it's still wrong, so I must have dropped it on the way out of the result or the operand register. Okay, so everybody got that? So the functional unit time is equal to the AI ready minus 1. I could have told you that yesterday, but that would have made it too easy. Load A1. Okay, that was the first instruction. Now notice how I didn't bother including any of the rest of them yet. We'll catch up with them later here. What was the next instruction? It's going to be in CIP at this time. Let me write the times up here. All right, CIP, what's the next instruction? It's an 030, 4, 5, 6. When this is in CIP, he says, are there any register reservations that I'm conflicting with? No, so he issues right away, doesn't he? Clock period 1. He reserves A4, gate A5 and 6. Release A1 here? Or A4 here, I mean? Everybody agree with that so far? At clock period 3, I'm in a function in it. CP4, load A4. Well, that was kind of neat, wasn't it? We issued this instruction 1 clock period later, but it finished a clock period ahead of the other one. Anything wrong with that? What enables us to be able to do this is the fact that we're sitting here with several different paths into the A registers. Remember, I mentioned that before. There's several buses into the A registers. So that I can load A1, it's got a separate and distinct path coming in from multiply, in other words, into the A registers, and there's another path coming in from an adder. I showed you on the block diagram there are two different places. There are two different functional units, and they have their own path. There are some exceptions to this rule. I'll get to them some point in time. But for right now, I'll just say that there's enough paths that everybody can do their thing. All right? Any question on that? Okay, the next instruction then. It's in CIP right here, the green instruction. It's another 030, but I don't remember the operands. What was it? 714. This guy's in CIP. He says, can I issue? Why not? A1's reserved. A4's reserved too, isn't it? There's two cases these can't issue. So he says, okay, I hold issue. Now, another little choice bit of information here. There is no signal called hold issue. There is, however, a signal called issue. There's an R term that you'll find on all of the control modules that says this is the issue signal. It's an R term. If you don't make that issue signal, which in this case we wouldn't, you create a condition called hold issue. In other words, we held issue from being created. Why? Because we had a request to use A1. Excuse me. We had a request to use A1 as an operand register, and we had A1 reserved. That by itself will drop that issue signal, or force it to be a 0. But we also have a request to use A4 and a reservation on A4 at the same time. So we got two ways to break it this time. So he says, nope, you can't issue. That means you recirculate. NIP recirculates, CIP recirculates, and the P register recirculates. So here we are in CIP, the next 9.5 nanosecond time segment, or clock period. And this time he says, okay, can I issue this time? No, why not? He says A4 is okay. Well, that's true. A4, the request to use A4 is still here. We made it again. It recirculated. And the reservation went away, so he says, oh, I'm ready to go. But then he looks at A1 and he says, oh, no, rats, I still got to wait one more clock period anyway. A1 still reserved, and I requested it. So once again, we drop that R term, R0 or 1. And we hold issue one more time. So that means we spend another clock period in CIP. Okay, now he says, this time, can I go? All right, so this time he says, I have a request to use A4. A4 is not reserved. I have a request to use A1. A1 reservation just went away. That brings up a special condition, doesn't it? What about A4? Do I have to bypass that? No, because next clock period I'm going to go and I'm going to say gate A4, and it's going to be there, isn't it? So there's no need to bypass that. But I do have to bypass A1 because it isn't there yet. So I go to, whoops, almost held issue there. So I go to clock period 1. I reserve A7 gate, A4, and that's the only one I gate because of that bypass. He says there's no need to gate A1 because It isn't there yet anyway, but it'll be there by the time you need it. Next clock. The A1's data comes racing in from the functional unit, goes into the register and into the readout register at the same time. So now we can run it to completion here. Well, that worked out kind of neat. I just happened to have enough clock periods up there. Amazing. Luckily, somebody come in and asked me a little something about it, otherwise I wouldn't have known. So the answer, I guess, is 8 clock periods from the time you issue the first instruction until A7 gets loaded with its data. The S registers have more functional units. The S registers are the ones you're supposed to use if you want to do adds and subtracts and logicals and shifts. The address functional units are used generally for address calculations. But if I want to add 2 and 2 and get 4, I can still do it down here in the address functional unit and get the same answer. But if I want to add 24 bits and 24 bits, then I better be up here if I want to get the right answer. All right, any questions on the S registers? The S registers also have the multi-bus capabilities. In other words, we can load S registers from the add logical shift, pop and leading 0, add and multiply all at the same time, if we want. If you write your instructions right, it'll do it. Now there are some small exceptions to that multi-bus path. And I give you those right away while I'm thinking about it. There are some cases where they said, well, we got multi-bus for everything except these 2 conditions. And here they are. Oh. Just choked myself. How do you spell exception? A register exception, this is it. You can multi-bus for all purposes except for you have multi-bus capabilities except when you do an O33 instruction and immediately behind it is an O27. And they said, in other words, the data for the O27 and the O33 share the data path in. And the O33 is 1 clock period longer than the O27. So if you did an O33 and then an O27, you'd have both data words coming back at the same time. And they would OR together unless we solve the problem. And the way the control is going to solve this problem for you, they're going to hold they'll hold the issue of the O27 for 1 clock period. So even though it's an exception, it's something that you don't have to worry about. Just be aware that there's a multi-bus for everything except for that one case. The hardware takes care of it, yeah, that's no problem. But that I said there was a multi-bus, but that's one case where there isn't a multi-bus. They share the same bus here. And if you wrote your instructions like this, it would still work, but it would take 1 clock period longer than you'd think because of that exception, because of the bus conflict we had. We said, well, we can solve that easy enough. If you have an O33 at clock period 1 and a CIP you have an O27, we'll just hold issue on the O27, 1 clock, and that solved the problem. Any question on that? So it was an exception to the multi-bus rule, that's all I'm saying. S register is the same way, but once again, the hardware is going to solve it But it's still a place where the multi-busing didn't work out. In other words, they didn't have that many places to, that many buses coming in, so they said, well, we'll share it for this one case and we'll solve it in the hardware like this. All right, so in 056 through in 061, all right, once again, well, the 052 through 055, I think that's some sort of shift operation. And if you did a shift operation and it was immediately behind an address or a scalar add operation, the shift and the add functional units share their data paths. And it so happens that the shift takes 1 clock period less than the add does. And since they share the paths, the data would OR if we didn't solve the problem. The way we solve the problem, they say, well, if you've issued an 052 through an 055, and you have in CIP an 052 to 055, and you just issued an 056 to 61, just hold issue on that for 1 clock. That'll solve the problem then. All right, any question on that? So the multi-bus is true except for those 2 exceptions. And those exceptions are solved in the hardware. You don't have to program in it. You don't have to worry about the problem. But you do have to realize that if you're writing a timing diagnostic or something, you might want to know that it's going to take 1 clock period longer than that. Any questions on that then?
This is the end of Section 3, ANS Registers. Please stop the videotape and read through the key points for Section 3 in your course materials. After you've read through the key points, complete the exercises, check your answers, and then restart the tape player to begin Section 4. Section 4, Vector Registers.
We got all the easy stuff out of the way now, so we can get down to the meat of the computer. And that is the vector registers. Actually, the vector registers are what make the XMP as fast as it is because of the way the vector registers work. Now, there are computers available that have vector capabilities that are faster than us, but it's a combination of the vector capabilities we have and the S register speed that we have that makes the cray 1S and the XMP line the big sellers that they were. The vector registers are just like the ANS registers. There's 8 of them. But they have one little tricky thing about them in that they're not only are they 64 bits in length, but they're also made up of 64 elements. So every time you do a vector operation, for example a vector add, you could possibly have 64 elements come into play. So if you take vector register 2 and vector register 1 and add them together and put them in vector register 0, you're not just getting one 64-bit answer back. You could be getting up to 64 64-bit answers back. So there's different parts of a vector register which we're going to call elements. All right, so every vector register is 64 bits in length, and it's made up of 64 elements. All right. The vector registers have their own functional units, just like scalar and address did. There's a vector add functional unit, there's a vector logical functional unit, there's a vector shift, and there's a population parity functional unit. They also have access to the floating add functional units, the floating multiply, and the floating reciprocal functional unit. They share them, remember, with the S registers. You can block load the vector registers from memory. And in fact, it shows the data coming back from memory, and it shows the address, the contents of the address here. And it says there's 2 read paths into the vector registers, and there's 2 and 1 write path. Now, unlike the B or T registers, on the vector registers, whenever you do the block load, you must start at element 0. You always have to start at element 0 of a vector register. But you don't have to fill the whole thing. We have something called a vector length register here. And this vector length register controls how many elements you're going to operate on every time you do a vector operation. So if you do a vector add and you want to add V2 and V1 and put it in V0, first of all, you have to set your vector length to how many adds you want to do. You can set that vector length to any number between 0 and 100 octal. So you can either do all of them, or you can do one of them, or anything in between. Any questions so far? The vector length register, however, is not like the block transfer for B and T's that we were talking about. The maximum value you can have in that vector length register is 100. And in fact, only 6 bits are transferred from an A register to the vector length register. What they do is they look at those 6 bits and they said, if the lower 6 bits are 0, you must have wanted 100. If the lower 6 bits are anything between 0 and 70, or 1 and 77, that's exactly what you get. All right? So in other words, if you try to set the vector length to 0, you end up with 100. You don't do no transfer, you do all of them. That's a little different. Let me say that again. Picture, it's called for here. What you do with the vector length register is you can load it from an A register. All right, so here's our vector register. 2 to the 0, or A register, 2 to the 0 through 2 to the 23rd. What we're going to do when we transfer this value, whatever it's equal to the vector length register, all you transfer is the lower 6 bits. So it says if you've got all zeros here, the vector length register says, okay, you've got all zeros, I can do that. But he says, oh, wait a minute, if these are all zeros, you must have wanted 100. And so I'll set it to 1. All right? So a value of 0 transferred from an AK to a vector length gives you the same thing as if you were transferring a value of 100 in there. Okay? Or 200, or 300, whatever you want to transfer. It says if the lower 6 bits are zeros, you get a value of 100, period. Now, if you have these set to something other than all zeros, you get exactly that. If they're set to 1, you get a 1. If they're set to 77, you get a 77. If it's set to 0, you get 100. Any question on that now? Is 7 bits. The actual register is 7 bits, but all you transfer from the AK to the vector is 6 of them. The least significant bits there too. Okay, now, once we get this vector length register loaded, let's see, what is this instruction that does this? I think this is a 002 instruction also. JK. Is that right? 0020. Let me check here. 0020 is 0K. In other words, it says transfer, well, let me do it right here. If you issue this instruction, it transfers the contents of a K2 vector length. All right. So when you issue this instruction, the 00200K instruction, what you get is whatever was in a contents of AK, the least 6 significant bits transferred to the vector length register. All right? Any question on that? That's all it does. Transfers 6 bits. Okay. Notice how the G and H is still the opcode, but they said you have to have a 0 in the I and J before this instruction will work. If you have anything else, you might get something different. All right. Let's see. Now, any question on that then? We also, I mentioned before, I said when you issue a vector instruction, before you can issue it, you have to check and make sure the functional unit's available. Now you can start to understand why you had to check on a functional unit. For that add operation we were talking about, we aren't just going to do one address or one add and take 2 operands, add them together and put them in the vector register. Because our vector length now is set to 100 octal, we're going to take all 64 of the elements out of vector register 2 and vector register 1, and we're going to add them together and we're going to transfer them over to vector register 0. All 64 decimal or 100 octal elements. So when even though that functional unit is fully segmented, you're using it for 64 clocks. So we're sending 64 different sets of operands over to that functional unit, and we're getting 64 different results out of it. And so for that reason, nobody else can use it until you finish this one address or this one add operation. All right. The same way with the logical or the shift or the floating multiply, add, and reciprocal. Because you have those capabilities, you have to make sure that the vectors aren't using it before you can use it with some other operation. Where in the floating point where you share them with the S registers, remember we had to check that. This is the reason, because you could have been doing a vector operation in those floating point functional units, and it takes a while to get it finished. Once this instruction then issues, you have to reserve both the operands and the destination register. Why? Because we're taking data out of the operands for 64 clocks. We aren't just taking out one operand, we're taking out 64. Takes a while. So when before an instruction can issue a vector instruction, you have to check the functional unit to see if it's reserved. You have to check all the registers to see if they're reserved. When it does issue, you reserve the functional unit and you reserve all of the registers involved in the operation. All right, this is the operation we were talking about. We're going to take V1 and V2, we're going to add them together, and we're going to put it in V0. Well, we said when we issued this, let me draw the data field on these registers. I'll make it in octal. 0 through 77 octal elements inside here. All right, when we're going to do this operation, what we're going to do is we're going to take element 0 out. We're going to transfer both element zeros over to the adder. We're going to start the add, latch it up in the middle of the adder here. I think it takes 2 clock periods. We're going to continue the add, be almost finished here when we're in the next latches. At the same time that we're here, there's the next element right behind us. We're then going to finish the add, and we're going to come over here and put it in location 0 in the result register. And then we're going to continue this for 100 or 64 clock periods, or 63 more, I guess. Now, if you think about this, there's a lot of things we got to take care of here, don't we? I mean, we have to keep track of which vector element we're going to send out. we have to keep track of which two elements, I guess, which element pairs. We have to make sure both of them are ready to go at the same time. We have to select one of these functional units, and if we look at the functional units, we've got 8 vector registers. We've got an add, a logical, shift, population parity, floating add, floating multiply, and floating reciprocal. So that's 7 functional units, and we can also send data to memory. So there's 8 different places we can steer one of these 8 different registers to. We said, that's too much to keep track of right here on this vector register. So what we're going to do is we're going to put some steering modules in between here. In other words, when we issue this instruction, we'll tell these 2 modules which functional or which registers to take out and send to which functional unit. Well, on the other side, we got the same problem, don't we? We got 8 different functional units that are going to be sending data to one of 8 possible registers. So the same thing applies. We have to put a steering module in here also. And this takes 1 clock period on both sides here. All right? So now we got to get all of these modules chained together here, first of all, for this operation. And then we got to kick it off and start sending the data. Well, if we've got inside these vector registers one of possibly 64 different registers, and I said we always had to start at 0, we have to have an address here for which one, don't we? So we got to have a little address pointer to tell us which one to take out of here and send off to the functional unit. Well, that means we need a little address pointer down here also. Well, if we've got an address pointer to tell us which one to take out and send off to the functional unit when, we also got to have it over here when we get it to tell us which one to put it in. So we got another address over here. Now, that's why we said, well, we'll always start at 0. That'll make our address easier. We'll come in here and we'll just clear it with a control signal. We'll clear all the addresses, and then we'll keep transferring the data until we're finished. But we have to know when we're finished, don't we? We have to have a block counter here, don't we? What did we call the block length of a vector operation? Vector length register. So we've got to have a copy of the vector length here, and here, and over here. So what we're going to do is we're going to make this a little incrementer. We'll just put a +1 on here. And we'll just keep taking elements out of element 0, and then 1, and then 2, and then 3, and then 4, all the way down. It'll just increment by 1 every time we do a transfer. At the same time, we want to decrement our vector length. So we'll make that a -1 counter. All right? So we can say we're going to be using vector register 1. Remember, our vector length is up here. We're going to take our vector length register, a copy of it, we're going to send it to V1, V2, and over to V0 so that they can keep track of when they're getting their, or how many words they're going to get yet, or how many words they have to send out yet. Every time we transfer one, we'll increment our address and decrement our vector length, our copy of it. But see, that didn't change the overall vector length that we had up here because we just grabbed a copy of it anyway and sent it to all those places.